Greetings for the day, Aarush Jain, and today I will be presenting a PPT on edge detection, which is one of the most foundational technique in image segmentation. So, when we talk about segmentation, taking an image into meaningful regions, which is one of the core approaches in detecting discontinuities, which can be sudden sharp changes in an image. And in this, one of the most important types that comes in the picture is an edge. So, So let's get to know about what is an edge, why it matters in first time. So an edge is a sharp local change in pixel intensity between two adjacent regions in an image. To give a good example, if we have a balloon on the table, the boundary where the balloon ends and the table begins, we would see like a sudden jump in brightness. That can be called as an edge. So now the question comes why it matters. Because in images, edges correspond to object boundaries. So finding edges is essentially finding where objects are. That's why edge detection is very central to segmentation. Uh, Now let's see pause by. Edges arise from the main source, depth discontinuities, where one object is in front of another. Surface orientation changes, difference in illumination, difference in surface reflection, etc. So to show a simple example on the right, you can see a simple intensity profile. On the left side, there is a dark region with low pixel values, and then there are some sharp spikes at the head location. And on the right, to the way the intensity high, the spike is exactly what edge detectors are designed to find. Go to the next slide. Yes. So now the question is, how do we detect these edges? One of the general approaches to scan a small mask or a kernel or filter across the image pixel by pixel. The mask is designed to respond strongly when it encounters the kind of discontinuity, that is edge, which we are looking for. So there are three possible discontinuities. One is point detection, line detection, and third edge detection. So when it comes to point detection, it is finding isolated pixels that differ significantly from their neighbors. This is one of our rare cases from a practice. Another is line detection. In line detection, we find one pixel wide lines to be horizontal, vertical, or diagonal directions. Then there is the edge detection. In edge detection, we find the boundaries between regions of differing intensity, and it is by far the most common and most useful. Here in the bottom, you can see a simple 3 cross 3 filter for point detection. The center weight is +8, and all 8 tables are -1. When this sits on a uniform region, the output is 0. But over an isolated bright pixel, the output is large, which points it out. So edge detection uses more sophisticated masks like gradient operators, which we will look further into gradient operators. So before here, I'm coming to gradient operators. Edge detection is fundamentally about measuring how quickly intensity changes. And the mathematical tool for this is an image gradient. Basically, gradient is a 2D vector. It's a GX and a X, where X or horizontal line, which measures the rate of horizontal intensity change, and GY, which measures the vertical change. At an edge, the magnitude of this vector is large, and in a uniform region, it's quite small. So we have three classic gradient operators: Roberts cross, Redwick, and Sobel. And the Roberts cross, this is one of the simplest ones. It uses a simple 2 cross 2 pointers and is computationally very fast. However, it is extremely sensitive to noise, which makes it unreliable for most of the real world images and applications. Then comes Previt. Previt uses a 3 cross 3 kernel, which considers 3 rows and 3 columns. Simultaneously, it averages out some noise and gives a more stable estimate. And finally, we have Sobel. In Sobel, it is the most widely used of the three. If we compare the matrices, in the Sobel one, there is like -101, -202, -104. Basically, what it does is it gives extra weight to the pixels directly adjacent to the center, making Sobel more robust to noise than Previt. And if you notice in all the kernel grids, you see green cells for showing properly. Green cells are positive and red cells are negative, and the gray are zero. The interplay between the positive and negative values means these marks respond to change in intensity rather than the absolute brightness levels. Let us see Laplacian and Hamiltonian derivatives. The first order graded operators work well, but they have a fundamental problem, which is the noise. So any small fluctuation in pixel values gets amplified and can be mistaken for an edge, which can be a very big. So it brings us to a second order derivative, which is Laplacian. Instead of looking for the peaks in the gradient, the Laplacian looks for the zero crossings, the second derivative. Why this is done is because at an edge, intensity rises very steeply. So it means that the second derivative crosses from positive to negative to exactly zero. That zero crossing marks the precise edge location. But there is also a catch as well. In the Laplacian fellow actually amplifies noise even more than the first operators. So the ultimate solution that comes is Laplacian of Gaussian or LOG, which was developed by Marr and Hildreth. The idea is that smooth the image within Gaussian filter. This is done to suppress the noise. Then apply the Laplacian to find zero crossings. The combined shape of the LOG filter looks like a Mexican hat, hence its nickname. The pipeline we see at the bottom is an input image, then Gaussian smooth, and then Laplacian and then zero crossing edges. Now, Canny edge detector. Uh, when it comes to Canny edge detector, this was developed by Sir John Canny in 1986, which is considered and still used a lot there. So, what in the filter that he did is he formally defined a good edge detector, which must be achieved and designed. For that, he designed an algorithm to satisfy all the three criteria simultaneously. Let's take a look at the three criteria. First is the low error rate, which is to detect as many real edges as possible with minimum false positive. No missed edges and no ghost edges. And criteria two is good localization. Good localization as in the detected edge pixel should be as close as possible to the center of the true edge. Then the third criteria, single response. One edge pixel per real edge. Basically, not a thick band of multiple detection. To see how the algorithm achieves this, there are four steps to it. The first step is Gaussian smoothing, which applies the same principle as LOG, which we had a look at right now, to remove the noise before doing anything. Then there is gradient magnitude and direction. Apply Sobel operators to get the magnitude and direction of the gradient at every pixel. Third is non-maximum suppression. In this step, we basically achieve single pixel wide edges. And in step four, hysteresis thresholding. Basically using thresholds to intelligently accept or reject the edge candidates. Let's have a look on this more properly. So non-maximum suppression. This is used in step three. So if we had a look, we had first computed GX device using Sobel. So now after computing the gradient edges, do not appear as thick bands, not just single edge pixel. But if there are whole over a neighborhood of pixels, we will get high gradient values. And if we keep all of them, our edge map would become very blurry and thick, which is not useful. So this is fixed using NMS, non-maximum suppression. It basically does is for each pixel, if like is the pixel the strongest gradient in its local neighborhood along the gradient direction? Does this. So to check this, basically we look at the two neighbors in the direction of the gradient, let us call them P and R. And if the current pixel is stronger than both P and R, we will keep it. Otherwise, we will suppress it, meaning we will set it to zero. Uh, to show an example, this is a grade 363595474. Before NMS, there's a band of high gradient values, which are centered on the actual edge. After NM, there is only one single strong. Then basically only one single strongest pixel survives. This results in a single pixel width. This is why Canny achieves such precise localization. Then the hysteresis thresholding we had a look at, let's move on ahead. And in the final step, step four, the problem with the single threshold is the classic dilemmas. If we set it too high, we miss the faint vertical edges, and if it has gaps or we set it too low, the noise generates and false edges appear everywhere. So this is where hysteresis thresholding comes in. So in this, we have two thresholds, a high threshold T high and a low threshold T low, which are basically in the ratio of 2:1 or 3:1. So what we do is first a strong edge, magnitude above a strong edge, any edge which has a magnitude above the T high. These are unconditionally accepted, meaning that these are definitely real edges. We have to keep it. Then there are definite non edges. If the magnitude is below T low, these are directly rejected. We do not need it. And and then there is a in between of these two, strong edge and not an edge, weak edge. It is accepted if and only if it is connected to a strong edge. Meaning if there is a real edge that is partially faint, maybe due to any reason like 21 by 8, or any other reason. But because it is strong, the V-gate would be good. So, but there is an isolated noisy pixel which has no strong neighbors and gets rejected. So basically, we get be accepted only if it's connected to a strong. So what this results is in a clean connected gap-free edge match. So if we have a look at the comparison next, so for all that we have discussed, let's have a comparison of that. In the robots, we saw very minimal computation, but very noisy, which was really beautifully alive. Second came Privet and Sobel. These are used a lot, which are good for most technical tasks and low computation cost. But stable, Sobel is preferred more for its noise robustness. Then there's LOG. LOG is the one above all these. It is better at noise handling through caution, especially and more precise as localization to 0%. And finally, we have Canny, which is the best overall winner if we compare all the five of them. Because it has the best noise tolerance, best localization, single pixel edges, but at the but it has the little disadvantage that there are more competition and a few and a extra more parameters to tune. So the key takeaway that we can get is edge detection finds large rapid pixel intensity. Second is we use image derivatives, first order for gradient magnitude, second order for 0%. Then the third would be the canny pipeline. Each step addresses a specific failure mode of simpler methods. And the fourth and final one, noise suppression, which every serious method smooths the image before differentiating. And finally, coming to the summary, to summarize, edges are sharp intensive and they encode the structural information. We need to find and understand objects in the images. So for this, we have a spectrum of tools, simple gradient operators for speed, LOG for precision, and canny when we want the test quality. So that is the end. Thank you.